I am just hitting the record button, everyone. So it's good to see you. Let me know in the chat, can you hear me out there? Smash that chat button. Hello, Steve. Let me know if I'm coming in loud and clear, everyone. Hello, Steve, Dijan, Yuhao, Ashwin, Brett, Eloisa, Aria, Menglu, and Carl. Hello. Now, the most important thing today is the lab test 1 has been announced, and there are practice tests. And what I thought we could do in Monday's tutorial is to do some questions from the practice lab test. Okay, so go and do them. Join me on Monday. The 4 people who I just put a poll up. 18 people said yes, it's a good idea. 14 people said no. 4 people said no, sorry. The 4 people who are not interested in revision, you could go to a different tutorial if you wanted to, or maybe you just watch the recording or something. Okay, so go and do the practice classes. And the most important thing, this is the window for doing the test. You got to submit the test, or you got to complete the test by 5 p.m. You cannot start the test at 4:55 and expect to have the full time to do the test, right? So don't do that. Okay. All right. So I hope you're enjoying the week this week, week 4. In today's tutorial lecture, we're going to talk about extrema, so maxima and minima, and so more calculus, and we'll end with L'Hopital's rule. So like much of calculus, some things will be familiar and some things will be new. Okay, all right, so I'm going to kill that survey and I'm going to share my screen with you. And here are today's notes. So let me know. Oh, Nicholas, I did get a haircut. I did. My wife cut my hair. Thank you for noticing. And that's a great that's a great avatar. Thank you. Thank you. So I'll pass that that comment on to my wife. So thank you very much. All right. So extrema and L'Hopital's rule. So I think this will look familiar. Extrema is just a fancy way of saying maxima or minima. Okay. So that's just a funny way of a sort of collective term for these two things. And L'Hopital's rule, it looks like L'Hospital's rule, but this is a French name, a famous mathematician who's credited, and it's got to do with taking limits. So it's a nice strategy when you want to evaluate certain kinds of functions and their limits. All right, so this will probably be familiar, this not so much. Okay. All right. Okay, so I think these will mostly be familiar, and this should be new. All right. Okay. Now, as you know, this is a calculus part of the course, and so we're going to look at these maxima or minima and investigate them using derivatives. So first and second order derivatives, okay? And the second thing we're going to do is look at L'Hopital's rule, and it's got to do with taking limits. All right, so let's have a look at first and second order derivatives and connect it with what we already know. So we know that if a function has a derivative that's positive on some interval, then we know f is an increasing function, right? So it goes up from left to right. If the derivative is negative, then it's decreasing from left to right. And if it's 0, then, well, it's just a horizontal line. So we're going to continue with this thought process in this lecture. All right. So the first new idea we're going to look at is the idea of concavity. And in particular, we're going to look at concave up or concave down kind of functions. Okay, so as a very simple drawing, a concave up function kind of might look like that. So I remember the u that from the up, and this sort of looks like a u, and concave down, you can think of it like that. Okay. Vina, sorry that you can't hear me. Maybe you can come in, pop out and come back in. I know you've been having a lot of trouble with your Wi-Fi and internet. I hope it gets solved. All right. So these two definitions here are all about concave up and concave down functions, right? So we're going to explore them through looking at the first order derivative. Okay, so concave up, a function is concave up on an interval if the derivative is increasing. Okay, so you can see up here, if I draw in little tangent lines, the derivative starts negative but slowly increases through to 0 and then positive. Okay, and what about concave down? Well, the derivative's decreasing. Here, the slope of the tangent lines are all positive, but they're moving towards 0 and then negative as we go from left to right. So that's one way of showing that a function is concave up or concave down. Just look at whether the derivative is increasing or decreasing on the interval. Okay, not the function, the derivative. Okay, that's really important. Now we'll be looking at a way of showing concavity with second derivatives, but let's look at an example first. Okay, so x squared. So let me just draw in the x squared function. And we can kind of use this, this idea here. If I just look at some of the tangent lines, here they're highly negative. The slope of the tangent lines are negative. But as we move from left to right, you can see the slope of the tangent lines are actually increasing. Here they're negative, here it's 0, and then it increases to positive values. Okay, so you can look at this from the graph, or you can just compute the derivative, right? So you can consider the graph, or just differentiate this and go, when is this function increasing? Well, it's increasing for all x, right? Because the graph of 2x just looks like that, right? And that's increasing for all x. Okay, so where is it concave up? Well, it's concave up everywhere, and it's concave down nowhere. Okay. Okay, so for all points, for here for the whole real line, the function's concave up, and it's nowhere concave down. Okay, so that's two ways of doing it. You can either consider the graph and the slope of the tangent lines, or you can just differentiate it and go, well, is this increasing, decreasing, and where? Now you can also use the second derivative test, because if the function, the derivative of the function is increasing when f dash of dash is positive, right? So this and this are the same. The derivative of the derivative is positive. And down here it's that. Okay? So let's say up here, let's say you had negative x squared, right? Then let's look at the second derivative. So the second derivative is going to be negative 2. So f is concave down for all x in this interval. Okay. What about another one? If f of x equals, say, e to the 2x, then the second derivative is going to be 4 times e to the 2x, which is always positive. F is concave down, concave up. Okay, so 3 ways now. Look at the graph, look at the first derivative and see whether it's increasing or decreasing, or look at the sign of the second derivative. This test is probably the easiest in my opinion, because you just differentiate twice and look for the sign. Now, in all of these examples, you've only got a function that's concave up everywhere or concave down everywhere. Okay, sometimes they'll switch. Sometimes they'll switch. So let me show you a picture of something where it might switch. Okay, I'll just put this into GeoGebra. Just give me a second here, everyone. Oh, okay. My GeoGebra is just frozen. All right, just give me a second. Okay, so if I switch over to GeoGebra now, I'll show you something here, right? So let's go with 2x cubed minus 9x squared. Oops. Okay. So you can see here that for x less than 0, the curve, the curve is going to be concave down here and then concave up here. So that's an example of a function where the concavity can change. Okay, so functions don't just always have one kind of concavity. Okay, all right. So let's continue. Now, critical points of a function should be reasonably familiar to you. You probably saw them at school, but in this course, we make 2 extra criteria for a critical point, right? So this is the kind of definition that most people remember from school. You differentiate and you set it equal to 0 and you solve it. And those points are the ones that are the critical points, okay? But these 2 are also important, and they're related to finding the maximum or the minimum values of a function. So they can certainly occur here, but they can also occur at these 2 situations. So this wider definition captures everything, right? So these things are a bit like Pokemon, right? You want to catch them all. And this definition that you saw at school doesn't necessarily catch them all, okay? So you want to catch them all, people, like Pokemon. So let me give you an example, and I'll show you what I mean, right? So let me just consider something like this. Okay, so here are my axes, and I'm just going to draw in a function here. So let's say I go like this, and then this. Okay, and this might be the 0.1, this might be the 0.4, this will be the 0.3, and this will be the 0.2. Okay, so in this picture, the endpoints of the interval are 1 and 4. By this definition, they're critical points, okay? Okay, so because this is an endpoint, and this is an endpoint of the interval, they're definitely critical points. Is there anywhere where our function is not differentiable? Yep, there's a spike there, there's a corner. So 2 is also a critical point. And there's another point here where the slope of the tangent is 0. In other words, this is satisfied. So these are the 3 different situations that you need to consider when you're finding critical points. At school, you probably just talked about this because you had very friendly functions to deal with. But this, and this are important. And what it means is, if you look at the picture, for example, you can see the maximum value of our function is there. The minimum value is there. And these other 2 points, well, they play a role, but they don't alter the maximum and the minimum value of the function, okay? But they might, in other cases, okay? So critical point, building on what you know, but there's 2 extra bits to it, where f is not differentiable and where you consider the endpoints of the interval, okay? Super, super important, people. Super, super important. Okay? All right. So what can we do with this? Well, I'm glad you asked. We can look at maximum and minimum values. And this has nice applications. You'll see some applied problems where you want to maximize or minimize the output with certain inputs. And we'll look at some questions around that. Okay, so let's have a look at these diagrams and see what we can make of it. Well, you can see that's an endpoint, that's an endpoint. So these will be sort of critical values there, or critical points. That's an endpoint, that's an endpoint. And if you look closely, you can see, well, the derivative's 0 there, it's 0 there, it's 0 there, 0 there, and it's 0 there. So they're also going to be critical points. Who can tell me in the chat, is there anywhere these graphs or these functions are not differentiable? Are there any points where, you know, these graphs are spiky or they have corners? Who can tell me in the chat? That's right, Alan, Anna, and Aria, and Aloisa. Junchen, these are nice friendly functions. Carl, these are nice friendly functions, right? They don't have any kind of jump or spike or anything like that we saw on the other page. Okay, all right. So this value here would be called a global maximum. Now, the reason is, out of all the points in our graph, this is the highest point, okay? And if we look here, this would be the global minimum. Okay. If we look down here, you can see, aha, the global max in this case occurs at the endpoint, and the global min occurs where the derivative is 0. So you can mix all of these things up, right? And when you have little turning points like this, they're called local max or local min. Okay, so an example here, that's a local max. And let's see if I can find a local min right here. Okay. So when we use the word global, we're meaning like this, like on the whole interval, this is the biggest or the highest peak, right? And when we talk about a global minimum, that's like the deepest valley or the deepest trough. It's the lowest value. Okay. And when you talk about local things, they're just sort of little peaks and troughs. All right, couple of questions in the chat. Matthew, is it considered the global max min if it is bounded within a certain domain? I don't really know what you mean there. Are you just talking about this interval here? Matthew? Yeah, well, it is because that's our domain, right? We don't know what happened to the function outside. We haven't drawn it. So, yeah. Abdul Rahman, can they also be called points of inflection? Point of inflection is kind of, you might have a situation where your curve looks like that, and you've got a 0 slope there. Okay. Nicholas, is the left hand? No, I wouldn't call it a local max or a local min. We would use these horizontal tangent lines to do that. That's a great question. Okay, so I wouldn't call this a local min. Yeah, I would restrict those to where the derivative is 0. It's a good question though. All right, Serena, why is it a local max and not local min on the top one? Sorry, not a local min. Thank you. That's what you're talking about, right? That should be a local min. Thank you. Good question. Haha, I just wrote it down wrong. Okay, so global means everywhere, or the whole interval that we're considering, and local just means in a neighborhood or a roundabout. All right. Now, I suspect that most of you will remember the second derivative test. If you haven't, then that's okay. Or if you've forgotten it, that's okay. So SDT, second derivative test. Now, let me go back to my big head for a minute. Now, students confuse the last part of the second derivative test all the time. Okay, so don't let it be you. They understand the first bit, the second bit, but the third bit is strange. Okay, so, oops, that's not what I wanted. Go back. So let me run you through that. Okay, if the derivative of the function at a point is 0 and the second derivative at that point is negative, then f has a local max, right? So it might be something happening like that, right? If the derivative is 0 and the second derivative is positive, then f has a local min. So it might be something like that. Or, yeah. The third case is when the derivative is 0, but the second derivative is not negative, it's not positive, it's 0. And the most important thing here is people go, oh, it must be a point of inflection. Oh, if the second derivative is 0, it must be a point of inflection. No, don't do it, okay? It might be true, but you don't know for sure, okay? You don't know for sure. So people do that and it's not true, okay? So in the third case, you need more analysis. Okay, so for example, if I had a function that was, let's say, x to the power 4, right? If you differentiate that and solve, you know it's here, right? And if you take the second derivative, you're going to get 12x squared, which equals 0 when x equals 0. But the thing is, that's not a point of inflection. That's obviously a minimum, right? So, you know, like we ended up with this, and this clearly is not a point of inflection. So when this happens, you need to do more analysis. Okay, that's really important. It's easy to fall into the trap when like you go, oh yeah, max, min, oh the other thing is an inflection point. No, don't do that. Don't do that. Okay. Yeah, Elena, I did. It looks like a kangaroo, but it's actually a quokka, as some people. It's actually a quokka. Hey, it's actually a quokka. Anyway, found in Western Australia. So don't get fooled by this third part. All right. So let's move on to some problems, and we can work out how we solve these problems, and then some applied perspectives. Okay. All right. Yeah, it's real. The quokkas are real. I love it how the chat has been hijacked by Australian animals now. I love that. All right. So so keep the chat coming, people. So this is a way of like a strategy, if you like, for determining absolute max and min values, right? Or global. Sometimes we use the word global as well. Okay. So absolute and global, they mean the same thing. So you work it out on the interval. Evaluate f at all the critical points, including the endpoints. People forget that all the time. Use the largest and smallest of the value. So you compare them, and then you make your comparison. So the easiest way to do this is just to do an example. Some of you may already be familiar with these. So here's a function. Here's an interval. Determine the absolute or global maximum and absolute or global minimum values. Okay. So let me draw this in GeoGebra, and we can have a discussion. All right. So here we are. Just takes a while to come up. All right. So we've got our function. So here's the function without the restriction to the interval, right? And here's the part of the function that we're interested in, or the graph. Okay. All right. So who can tell me on the chat at what x point does the global or absolute minimum occur, and at what x point does the global maximum occur? Smash that chat button, people. Tell me about it. Tell me about it. Come on. All right. Nicholas, 0 and 3. Yeah, that seems to be the consensus. You can see down here, this is obviously the lowest point. And over here, that's obviously the highest point. Okay? And you'll notice that the function is not differentiable because there's a spike. And it's not differentiable there either because it's an endpoint. So this is the situation where we're actually determining global max or global mins, and we're not using calculus at all. Okay, we're not using calculus at all here. Okay. All right. So what would you do with that question, and how would you solve it? Okay. So let's evaluate the critical points, right? Okay, so the endpoints and the points where the function is not differentiable, that's at x equals 0, and that's it. If we go back to the main graph, let me just share that with you. Here's the whole graph without the restriction. So let me just share that with you. So there it is. You can see, sure, there is a point where you have a horizontal tangent, but that's at x equals 4. We don't care about x equals 4 because all we want is that bit, right? So there's no point where the derivative is 0 in between negative x equals -1 and x equals 3. Okay, so sure, there's a tangent, a horizontal tangent line, but that's out of scope because it's not in our interval. Okay. All right. So now let's evaluate f. So f of -1. What's that going to be? Well, that's going to be that. Of course, you could just read this off the graph if you wanted to, but let's just do it this way. So it's going to be 1 plus 9, or 1 plus 8, sorry, f of 3. That's going to be 3 squared minus 8 times 3. Yep. So 9 minus 24. So it's going to be something like -15. And finally, 0. Okay. So the last step, and again, some of you may find this super familiar. We want to compare these three values. That's the biggest, that's the smallest. Okay. So hence, the maximum of f on the maximum occurs at 3. And the minimum of f is, that occurs at 0, right? Ta-da! Da, 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 da. That's a 3, believe it or not. Okay. Now, the biggest mistake that students make is that they forget the endpoints. They go through, they differentiate it, and they just, they come up with something or nothing, and they don't know what to do. Calculus will not give you these results, okay? We didn't actually use this third bit. We just used these two things, okay? So just be mindful of that. You probably, some of you will have seen it, but maybe not everyone, okay? All right. So what can we do with this theory? Well, I'm glad you asked because it's very theoretical. Yes, it is. So let's look at an applied problem and see how we go. All right, before we do an example, let's look at strategy, right? So this is, again, strategy. Okay, so a basic rule or some ideas is to, we're asked to maximize or minimize something, right? So you want a relation between the things to be maximized or minimized. You want a function of one independent variable. So you start off with something like this, you simplify it so you've only got one variable, and then you want to apply calculus, okay? Look, find the critical points, evaluate the function at the critical points, and then compare them, okay? All right, so let's have a look. Let's have a look. Yeah, okay. So this is a classic example. I think it might be in your course pack, this question. It might be one of the tutorial problems. But I thought it was interesting because we can talk about it in lectures and things like this. All right. So you've got a piece of wire which is 1 meter long, and you want to cut it into two pieces. The first piece you make into a square, and the second piece you make into a circle. And the question is, how should I cut the wire so that the sum of the areas will be a minimum? Okay, so let's draw a picture first, and we can work through it. Okay, so let's say that's my wire, and I want to cut it into two parts. Okay, let's say X and Y. Okay, and I'm going to bend, the first part into a square. So if I do that, it might look something like this. And the second part is going to be bent into a circle. Okay? So the area is just going to be the area of this square plus the area of this circle, right? Okay. So it's pretty easy to get the area for the square. That's just going to be this. And the area for a circle, we know that that's that. And we know the area for that is just pi r squared. So to put that in terms of y, it's just going to be pi times okay. Okay, so where are we with our thing? Establish a relation involving the thing to be maximized or minimized. Well, that's it. Okay, I haven't simplified everything there, but that's it. Okay, and so what we would like to do now is form a function of one independent variable. Okay, so we haven't used this yet. So what I'm going to do is make everything depend on x, and I can do that by removing the y out of here and let y equal 100 minus x. So that's my relation. I've done the first part. I'm going to do the second part now. Okay, so from above, the area is just this. Okay, so all I've done there is I've replaced y with 100 minus x. Okay, so that is now my function. Hooray! All right, let's look at the turning points. Okay, and critical points. So this is a nice friendly function. It's a polynomial, so it's going to have a derivative everywhere. Okay, and let's differentiate it and see what happens. Okay, so I might just simplify this first. So I'm going to get 100 minus x squared, and it's all going to be over 4 pi squared, which will just be 4 pi. All right, so I'll differentiate this. Now you could simplify that. I'm just going to differentiate it. Okay. So dA dx. Okay, let's differentiate that. Well, x squared on 16 is going to become x on 8. This part, you can use the chain rule or you can expand it. The 2 is going to come to the front, the negative 1 is going to come to the front, and you decrease the power by 1. Okay. Yeah. So now it's just setting that equal to 0. Thanks for helping each other out in the chat. Okay. So you want to solve this for 0. So you can put this all over one denominator if you want to. Okay. So you want to solve it for x. It's just a linear equation. So the solution you get is this. Okay, so you've got a value for x now. And now you can put that back into your original relationship between x and y, and you'll get your y value. Okay, so that goes in there, and you'll get this. Okay, so how should I cut my wire? Well, x, you should cut it with this cut here and this cut here. Okay, so you can kind of see x is going to be slightly bigger than y, okay? Because this is going to be what, about 314, this is 400. Okay, so my initial picture isn't super accurate, but you get the idea. Okay. All right. Lastly, we want to apply the second derivative test. Okay. The idea is to show that d squared dx squared is negative. Okay, so when you differentiate this again, this will be an eighth. Sorry, it'll be positive. Sorry. Okay, so when you differentiate that, this will be a positive 1/8. This will be positive 2 on 4 pi. So by the second derivative test, we have a minimum. Ooh, took me a while, but we got there. Now, hopefully you can see that there's plenty of places here that you fall over, right? Like you can't get started with the initial relationship, or you can't remember the formula or combine them. There's lots of places where you can fall over here, but the ideas are basically the same, okay? Get a broad relationship, narrow it down to a function of one variable, and then apply the second derivative test, right? Find the critical points, etc. All right, so not particularly easy. All right, let me quickly show you how we can count zeros of functions, and then I'm going to move on to L'Hopital's rule. Okay, L'Hopital's rule is very different. Okay, so in this question, and I've added this extra bit in here, so this might not quite match your notes. Determine how many real numbers in this interval satisfy this equation. All right, so what we've learned to do in the past is use the intermediate value theorem, right? A function is a polynomial, so let's assume that it is defined here. Okay. It's negative at 0. So if I put in 0 there, it's negative 1. And if I put in 1 here, it's going to be negative 7, 5. It's going to be 4, I think, right? So 2 minus 9 plus 12 minus 1. It's going to be 4. Okay. So you know it's negative here and positive here. The intermediate value theorem okay, the ST stands for such that, right? But the question really isn't asking you this. It's asking how many real numbers in this satisfy the equation. So how many C's are there? All right, well, if we go over to the GeoGebra, did somebody say GeoGebra? Here it is. Okay, so who can tell me in the chat how many solutions does this problem have between 0 and 1? How many solutions? It has exactly 1. Yes, it's not a trick question. Okay, so how do we do it? Well, we can show that the derivative of the function is positive. Okay, so let's differentiate this and see what happens. 6x squared minus 18x plus 12. Okay, so what I'd like to do is show that this is actually an increasing function. It's having a positive derivative. And what I can do is go, aha, okay, well, that's just that. And I can factorize this, right? So Two numbers that multiply to give +2 and add to give -1. Okay. Now for x in here, that's always negative. Oh, sorry, 2. That's always negative, and that's always negative. Okay, so a negative times a negative is a positive. Okay. So that, if you're asked to do that, that would be some of the explanation that I would be using. You've got a function that's increasing, right? If it's increasing, can only go through the axes once, right? At most once. You know, from up here, there's at least one place where it cuts the x-axis. So combining these two, you know, there has to be exactly one. The exactly one, right? The intermediate value theorem, Captain Bill on the case. IVT, Aiden, you down with IVT? Yeah, you know me, right? IVT, yeah, you know me. You down with IVT? Yeah, you know me. How is only one solution? What do you mean, Russell? Speak up, buddy. How is it only one solution on the graph? Well, if I go back to the graph, it's not a dumb question. It's a really good one. Okay, there's only one place where the function crosses the x-axis. That point is where the function equals 0. Okay. Can you see that, Russell? That's the horizontal x-axis is equal to y equals 0. So Joyce, we just proved it, didn't we? In my notes, how do we know that the derivative is 0? It's right here. Because when x is between 0 and 1, that's negative, and that's negative. A negative times a negative equals a positive. A positive, Joyce. You got it? Yeah. Yes, Russell. Exactly. If it only cuts the x-axis once, it's only got one solution. Exactly. You got it. We didn't find the value of C, Nicholas. Good quokka picture, buddy. We didn't find the value of C. But yeah, but I mean, is it easy to find the value of C? It's not always easy. Sometimes it's easy, but it's not always easy. Okay. In fact, there are some equations where it's impossible to accurately find the value of C. Okay. Yeah. Look, we'll look at L'Hopital's rule yesterday because I've run out of time today. But we'll do that tomorrow. Sorry, L'Hopital's rule. But if you want revision on Monday for class test 1, I'll do one in the tutorial. Okay, in the tutorial. So some people, maybe, you can go to a different tutorial if you don't want it. But yeah, let me know your thoughts. Do you want a revision tutorial for lab test 1? Do you on Monday? Let me know. Comment for Quokka. Do it for Quokka. All right. And if you don't, that's okay. Just go to a different tutorial. All right. Thanks, everyone. I'll sign off. Let me know what's happening in the chat. I'll just turn the microphones on, just in case somebody wants to, smash out a freestyle rap or something. Feel free to ask your questions. I'll be here for a couple of minutes before Captain Bill takes over. So thank you. Namaste. Enjoy the day. And see you tomorrow. Let me know if you have any questions.